Here are the three Laplace transform problems that I'm going to do today. Laplace transforms have many aspects, and I'm only going to touch on the basic idea today. So let's get to the first question. The quickest way to work out a Laplace transform is normally to use the tables that you will be provided with. But in this first question, we're asked to work it out from the definition. So a lot of times in high school you would have been used to a function, say g of x equals x squared, and that takes a number, say the number 2, and it transforms it into another number, 4. What the Laplace transform does is a little bit more complicated. It transforms a function to another function. So we normally use this funny L to indicate the Laplace transform of a function f of t, and what we'll get out of it is this function f of s. So we use the big F to indicate that it's been transformed, and you can see that the t, which we had before, is now we've got an s, and the formula is just shown here. So you just take the integral between 0 and infinity of e to the power of negative st times f of t dt. So let's see how that works with our problem. We had f of t equals 5t, so if we want to work out the Laplace transform, we're going to just drop it in the formula up here with the integrals. And you can see right down the bottom here we have actually ended up with a function in s, as we would expect. So if we return to the top up here, we can take the 5 out of the integral. And now we're faced with a classic integration by parts problem. And a lot of these, if you have to do them from the definition, will involve integration by parts. If you're not familiar with integration by parts, you might want to have a look at my YouTube video, Integration by Parts Made Easy. Some of my YouTube videos are very popular. They're top on the YouTube search, but this is not one of them. So you can have a look at this one, which I think is very good, or you can have a look at many of the other integration by parts videos that are on YouTube. But anyway, in any shape or form, you integrate by parts and you get this line here, and then we just sort of simplify it all out and we get 5 on s squared. Now normally you'll be given tables and you won't have to go through that. There are a couple of Laplace transforms that we'll just mention at this point which we'll need, and you can get them normally off the tables. The first is the Laplace transform of the derivative of a function f of t, and we would normally be expressed something like this. And it's also sometimes useful to know the Laplace transform for the second derivative, which often will be in the tables as well, and I've put it here. In this second question, we haven't seen yet what this L with the power of -1 means. It's the inverse Laplace transform. And you've probably seen inverse functions in your studies, but if I just go back to question 1, we can explain it with this example. We saw here that if we have ft equals 5t, the Laplace transform is 5 on s squared. So we say that the inverse Laplace transform of big F is equal to f of t, where f of t is equal to 5t. So if we now return to the problem that we're asked to solve, we can see that we can't just use the Laplace transform tables to work out the inverse here. But what we can do is recognize that this fraction actually up here can be expressed with the denominator as the product of s plus 1 and s plus 4. And now we can use the techniques of partial fractions. Now at this point you're probably saying, I've got a click on here where you can click through to my video, Partial Fractions Made Easy, but I don't have one, so if you don't understand partial fractions you'll have to look elsewhere. But the basic idea is that we express the fraction as a on s plus 1 plus b on s plus 4, and we want to solve for a and b. And we can cross multiply. We get down to this line here where we've simplified it a bit. And obviously here we've got a plus b times s, and on the left hand side we've just got 1 times s, so a plus b must equal 1, And we also know from here that 4a plus b must equal 5. So we have two simultaneous equations, and that gives us two unknowns. Well, we've got two unknowns, two equations, and so we can easily solve it. We get a equals 4/3, b equals negative 1/3. So now to return to the problem, this would be a solution, the inverse Laplace transform of the original fraction. We can now say it equals the inverse Laplace transform of what we've worked out from our partial fractions work. We can split that up into the two inverse Laplace transforms. And now this one here, the 4/3 can come out the front, it's just a constant, and we now look up the tables to see that the inverse Laplace transform of 1 on s plus 1 is e to the minus t. And with this one here, we take out negative 1/3. It's a constant, and the inverse Laplace transform of 1 on s plus 4 is e to the negative 4t. And that gives us our solution. Here's the third and final question. And here we see one of the really beautiful things about the Laplace transform, and that is that you can use it to solve differential equations. So here we have a differential equation with some initial conditions. And I've put here something from the first question we saw at the end of the first question, which you'll be able to get from the tables, which is the Laplace transform for the derivative and the second derivative of a function. And then finally down the bottom here I've put the answer from question 2, which we're going to need, and I'm just going to shrink that now so that we can fit in the solution. So we start off with our differential equation, and you can see here that our differential equation is terms of the function y, or y of t. And that's no problem. We've been talking previously about functions of f, but that's fine. We're just changing a letter. Okay, so we take the Laplace transform of both sides, and we've seen before that these Laplace transforms, you can break the brackets for addition and also multiplication by a scalar. So I've broken the brackets here, and now the problem is I've got this Laplace transform of a second derivative and a first derivative, which I want to get rid of, and this is where I use these results which you can get from the tables. So I can replace, here you can see I can replace the second derivative with just the Laplace transform of the function and some other things to do with the initial values, and I can do the same with the first derivative. So I can now replace the Laplace transform of the first and second derivatives, and I know what, for example, this term is y0. I know what y-0 is. I know this y0. So once I replace all of them with the initial conditions, I'm left with the Laplace transform of y is equal to s plus 5 divided by s squared plus 5s plus 4. Now I take the inverse Laplace transform of both sides. If you like, I get y equals the inverse Laplace transform of this fraction, and that's exactly what we worked out in question 2. So we can just put in the solution. Y equals 4/3 e to the negative t minus 1/3 e to the negative 4t. So we've only scratched the surface of Laplace transforms, but notwithstanding that, that's it for Laplace transforms made easy. I hope you found it useful.